Chapter 5, Quantum Considerations. Quantum field theory is a mathematical formalism that combines special relativity and quantum mechanics into a series of actions generated by various fields. Particles are treated as excitations of underlying fields, and the dynamics of these fields are described through the actions and their variations. The Lagrangian is similar to a metric solution in general relativity, as it is up to you, the theorist, to define it according to whatever particle, interaction, or symmetry you're trying to describe. QFT possesses an immense amount of predictive power and is often regarded as the most successful theory in the history of physics. Because it is a field theory, it must deal with any fluctuations, disturbances in the fields. Because these are quantum fields, the Heisenberg uncertainty principle forces every quantum field to fluctuate at all times. The effect can be computed, but the integrals over all possible momenta create infinitely divergent results. Renormalization refers to the procedure of assigning cutoffs to some energy scale. The physical charge from that scale serves as a reference point. Loop corrections are then adjusted, allowing the infinities to be managed, and the final prediction is made. General relativity introduces infinities that cannot be tamed with standard renormalization. There are no known cutoffs for the energy scales. There are many proposals to resolve this problem, such as string theory, supersymmetry, and loop gravity, but none of them have had satisfying results. Vacuum energy density. Vacuum energy density refers to the energy present in empty space due to quantum fluctuations. In earlier chapters, we established that the vacuum is not empty and is filled with mass and energy at all locations. In QFT, the vacuum is considered to be the lowest possible energy state, which must be some non-zero value. However, as we have repeatedly emphasized in previous chapters, mass density is a scale-dependent variable. The same principle applies to any energy density. The concept of a lowest possible energy density is entirely valid, but it must be understood with the proper context. Energy density is very high on the smallest scales because that is where all of the stars reside. It is entirely possible to cherry pick a void, and you will find a low energy density there. But generally speaking, the smallest scales are incredibly dense. The vacuum catastrophe is an enormous discrepancy between the theoretical vacuum energy density predicted by quantum field theory and the observed value from cosmology. In QFT, vacuum energy density is defined as the energy of the quantum vacuum per unit volume. It is calculated by summing the 0-point energies of all quantum fields for all possible modes. Our methodology requires us to abandon the substantialist perspective and redefine it. Here, vacuum energy density is not a fundamental property of space itself, but rather the minimum gravitational energy density for a given volume. In Chapter 3, we match the observed Hubble constant at 1 megaparsec to a gravitational redshift, giving us a fixed surface density, K equals 0.833 kilograms per meters squared. And from it, the radio profile. Rho of R equals 3 times K divided by 2R. A larger sphere always yields a lower average density, yet the curve never reaches zero. Mass density is inversely proportional to the given volume. Two natural length scales also emerge from this formulation. The first is the horizon distance, or roughly 1.3 times 10 to the 26 meters, around 13 billion light years. Beyond that, light is redshifted to the point of unobservability. The second is the emission point of the Hawking quanta that we interpret as the 2.725 Kelvin microwave background. Working the blue shift formula backward gives us 2 Planck lengths. If the quanta started any closer to the horizon, their temperature would rise and overshoot the data. These two numbers, the emission point of the Hawking radiation and the horizon, these two numbers therefore act as a built-in infrared and ultraviolet cutoffs. A textbook vacuum integral adds half a quantum of energy for every possible mode length and therefore diverges. Here, the sum is finite because modes longer than the horizon or shorter than the emitted location of the Hawking radiation are not observable. For the UV, we use 1 divided by 2 Planck lengths, and for the IR, we use 1 divided by the horizon, which gives us Pvac equals h bar c divided by 16 pi squared times KUV to the power of 4 minus KIR to the power of 4. The raw number is huge, but each shell of the radius r also carries the gravitational redshift factor. Multiplying the two value gives us ρvac square root of 1 minus r divided by rh equals 3k2r. Exactly the profile we started with. The apparent infinity cancels out shell by shell. Because nothing divergent survives, there is no spare term to be relabeled as lambda. One can still fold the renormalized vacuum piece into a formal cosmological constant, but it adds nothing new. In short, once we respect the two natural cutoffs supplied by the horizon and the emission of Hawking radiation, quantum field theory and general relativity no longer lead to non-renormalizable divergences. There is likely a ton of work to do philosophically, but this is the way.